Yeah. So we should certainly begin with thanking the organizers for such wonderful conference with the number of people, and that also seems to be online possible too. Yeah, so let me just say some stories about how I arrived on this kind of questions. So this is about 10-15 years back. We are trying to do, myself and Subramanian were trying to do some computation of the slopes of subbundles after polymax. So when we're trying to do that, we realize that it depends on some certain property of the spool max. So then it turned out that we were tracing it purely in terms of sheaf theory. But later we realized that it is nothing but just a topological property. So we state all those equivalents and proxima as time passes. And later we use this to, so this process is essentially used to certain kind of fundamental thing defined on certain spaces and comparing for a maps. So it's essentially for maps. Okay. So let me begin with just simple complex analysis, some properties. And some of the statements are actually even not even for curves in characteristics, even over complex numbers. Some statements will come later. Yeah. So let me begin with some little bit of complex analysis and some definition of Riemann surfaces, some maps, which are those probably even not doing any algebraic geometry or any other. So people who are actually in other fields too can follow for this. Let's say about first 15 minutes. Okay. Yeah, so let's begin with just looking at what is an analytic map. Okay. So I believe everybody understands what's a complex analytic disk and what is an analytic map between them. So let's just recall some simple properties of analytic maps. So an analytic map is actually an open map. So this is unlike when you do the real maps where C infinity maps and so on, the maps could be really very, very degenerate. While analytic maps are pretty nice. So it has got the bad things have got its own good properties. We'll see that. So they're actually open maps. Not only that. So when I take the maps, the fibers are actually discrete. You can't have a fiber which has got a limit point there. So this is an analytic map for a complex disk. Okay. So that in particular says the zeros of functions. So you can assume the image value is 0, then the zeros of the function are actually isolated. Okay. So, and a general map between the disks is going to be of this kind. So on any domain, if I look at the map, in a small neighborhood, you can write down a map like f z equal to z power n. So practically, locally, analytically, these are only maps. Okay. So all maps are like z goes to z power n for some n, depending on the point. And some places n will be 1, some places n could be 0, that means it's a constant map. And then you will see that it has to be constant all over. That whole connected component has to get collapsed. An analytic map cannot happen that there is a disk where everything is, or some big open place where it becomes 0 and the rest is kind of nice. Such thing will never happen. So these are the properties of analytic maps. Now, what do I mean by a Riemann surface? So Riemann surface is nothing but it's built up by the complex disks. So what is the condition? Maybe I should just give a pictorial representation just like that. Okay. So you have got a disk. So okay. Okay. Yeah. So you have a topological space and you have this complex disk. So you have a point in a small neighborhood, you have a homeomorphism. Suppose you have another point where there is another open set where there is another homeomorphism. But look at this. So this portion will come somewhere on the bottom here. And this portion for this, it will come somewhere here. Now, by composing, I come here. No, I use the inverse. From here, I come here. Think it as a point on the lower disk. Now think it as a point on the upper disk. I get a map back to the lower portion of this. So I get a map between two regions in a complex disk itself. I can demand that to be analytic. So a Riemann surface is got by patched up by lots of disks. And whenever there is an overlap happening between two such, the induced map on the disk, see, only on complex disk I can talk about analyticity. Here it's just a topological space. But if you have all these patches happening, then you can see that there is some kind of nice complex structure itself is carried on your X. And that's a Riemann surface. And this is actually a special definition of, instead of the D, I can take Dn. Then I get complex manifold of dimension n. And if I just take the real ball, I get real manifolds. And if I demand this, whatever the properties on this is called the transition functions. So whatever the properties that we demand there, if I just demand homeomorphism, I'll get a topological manifold. So this is how you define a manifold. Okay? So on a special case of when it is complex analytic, and with the dimension 1, it's called Riemann surface. And in higher dimension, it's just called complex manifolds. So yeah, so the complex manifolds, Riemann surfaces are complex manifolds of dimension 1. Now, let's look at some examples. I'm saying the sphere is a complex manifold. So this is the first non-trivial. So always people use this, have seen that P1, projective line is what they call it. So that's what is the sphere S2. Oh, yeah. So to see this, one way to see this is like, you just take, sphere is like this. Take the one point out, the north pole out. Then outside that, it is a C. Take the south pole out. That's also like a C. So I can give a homeomorphism from C to C. So from here, I give a homeomorphism C. From the other part also, I give a homeomorphism C. And on the intersection, you will see the map is really given by 1, Z goes to 1 by Z, which is an analytic isomorphism on C star. That's precisely the intersection. So this gives you the structure on P1. And next example is like the torus. So these are the first two non-trivial examples. Sometimes these are also called elliptic curves for different reasons. It's actually S1 cross S1. And as I have written down, so there are many more ways of seeing this. There are many different S1 cross S1s as a complex structures. But one of the trivial one is you take the plane and take all the integral points and just identify them. Okay? So you have got this minimal one. This is 0, 1, 1, 0, 0, 0, 1, 1. So you just identify on this square, you identify. So that is why when you identify this line, I get a circle. When you identify that, I get other circle. And you will see that when you do the identification, what you get is S1 cross S1. That's what is called torus. Okay, so that is another complex analytic manifold because there is already a map from C2 to C1 to S1 cross S1. So I can take some point here and the disk, I can give the disk to be this itself. the small neighborhood, you will see this is always isomorphism. Okay? So this is called so-called universal covering space. Okay? And then there are curves of higher genus. Okay? So there are many other Riemann surfaces. So we'll see some properties of that, because now I'm also trying to motivate a little bit about how the ramification comes and what is the impact of that. So let's look at a little bit on topology, and then we will come back how they are affecting for maps and so on. So here, of course, this is a trivial exercise to begin with. You can start with a compact Riemann surface, pick up some points and join them by some lines and take those triangles inside. This is what is called a triangulation. Okay? So you can, for instance, if I take this sphere, there's one easy way to do it is like you pick up 3 or 4 points. 1, 2, 3, 4. Not this, I've taken this. So you'll see that there are pieces which are like triangles. So there are 4 pieces of triangles, and similarly there will be 4 triangles below. So it's given by a bunch of triangles, which again there is some conditions how you do these triangles. So when I take 2 triangles, the intersection either should be a point or actually a face. So there are some conditions. That is why I put in quote unquote triangulate. Not just putting arbitrary triangles, but triangles have to be put in a nice fashion. Should be a nice kind of packing. Okay. So then it was known to Euler. So it wasn't very clear. I mean, at least I don't know, maybe within somebody else might know that it was clear to him that this difference, you take the number of vertices minus the number of edges plus the number of faces. However you do it, you are going to get the same number. And it's called the Euler number. Okay. The present day proof uses a lot of homology and a lot of simplicial homology, singular homology, some equivalences. So we won't get into that. So on this last one, it's just combinatorially given an object. Once I do the partition, I get this number. But that's already an invariant. It's an Euler characteristic, which is also written as twice minus twice of gx, and that gx is called the genus. So there are many other interpretations about genus, but this can be taken to be one, which is very simple to explain. Now let's look at maps. So what kind of guides when there is a map or not? So you'll already see that there are lots of restrictions. You just can't have a map. For instance, you cannot have a map from the sphere to the torus. So there are many such things. So we'll just see. It comes out of very simple combinatorial computation. Okay, a map of Riemann surface is a continuous map because after all it's a topological space. It should be a continuous map. But when you restrict to those places where you can genuinely talk about the analyticity, they should be analytic. Okay. Okay, so the last sentence that I'm going to explain a little more, just to get a feeling about the maps. Okay. Now let me introduce the word ramification. So my talk is about genuinely ramified maps. So first let me say what is ramification. And we will talk about the genuineness later. Okay. So what is ramified? For a Riemann surface, a map is ramified if the differential is zero. Okay. Or equivalently, a map expressed as f(z) equal to z power nx. So for every x, I told you, because it's a holomorphic map, for every point, for x, there is a number in x, where that local map is of the form z goes to z to the nx. So it's ramified if nx is strictly bigger than 1. So locally the map should look like not z goes to z, which is an isomorphism. But if z goes to z square, z cube, z power, any other powers, they are called ramification points. Okay. number is called ramification index. That at that point, if n to the nx, if that nx is 1, the ramification index is 1, which is like an isomorphism. 2 onwards, they are the ramification indices. And the set of all image point of the ramification is called bracket point. Anyway, I just gave it for definition, I will not going to use it. So now I'm going to just look back about how to get the triangulation. So suppose I had a map. So this is very easy to convince that there is a restriction, there is a very stringent condition when to have a map. So you have a space X and you have the space Y. That is, both are Riemann surfaces. Okay. So on here you begin with a triangulation. So you have triangulated this space. So you put it as bunch of triangles. Now I'm saying, look at these points. Okay. So look at a point here. Okay. So you may assume, so first of all, it's a compact Riemann surface. The zeros are isolated. Even the powers, so when this z goes to z power n, so there are also the zeros of those. So they are isolated. And then you will see that there are only finitely many ramification points. Okay. So there are some finitely many points here, which are, let's say, ramification points. Outside that, there is no ramification. Now look at its image. What I would assume is that those points are in the triangulation. If it is not there, suppose there is a point which lies here, it's very easy to make a new triangulation out of it. You can put some extra triangles with that as a vertex. So I will get a new triangulation with that also as a vertex. So you assume all the branch points are vertices. Okay. Then what will happen is, if I take a line here, this is, so outside these ramification points, this is actually a nice data map locally. So if I take such a line, I will happen, suppose this point lies here. So for this line, you will see that there is exactly one line. Not only that, for these points, there may be many points. So there may be many ways to join each of them. We don't know how many, but what we'll see that is this triangle has to pull back to a triangle. And a line has to pull back to a line, joining two independent vertices. So what happens is, if I made a triangulation here, I can take the induced triangulation up there by just pulling up these triangles, which contains all the ramification points. So somehow I make a triangle. Now I start counting the numbers. So the number of vertices, I don't know, which is some number. But what you can see is that suppose this map has degree d. So that is, suppose a general point has d points lying above. Then what you can see is, for every line, there will be d lines. And for every surface, for every triangle, there will be d triangle. But the points is a bit tricky. That the number of points may drop. Okay. So that's what I'm going to say next. Okay. So the vertices, if V, E, F are the vertices, edges, and faces, okay, then D, E, D, F are the edges and faces when you go up. But now you look at what happens. See, if this is not a branch point, then there are exactly D number of points. But suppose one point became a branch point. So suppose this was a branch point lying above this. Let us look at locally this map. So this map is of the form Z goes to Z to the nx. So let's call this point x. Okay. So what will happen is that look at this map locally. Z goes to Z to the nx. So that means over 0 there is only one point. All nearby, they are the roots of unity. So they are exactly nx of them. So the number of nx points, generally, I will take only one point. So what happens is, for every ramification points of index, the ramification index nx, I only take nx minus 1. No, I only take 1 point. That is, the rest of the nx minus 1 point is not taken. So that means you take the, so when you look at the Euler characteristic, what happens is, Euler characteristic was V minus E plus F. So the E and F were got multiplied by D. But the vertices, if you multiply by D, then I have to subtract nx minus 1 everywhere. That's what is called the Hurwitz formula. So the D times Ex minus Ui is actually the number of Ex minus 1 summation. So this gives very stringent restrictions on the maps. Okay, and about the genus again, comes as twice of genus of Y is twice D times genus X plus summation Ex minus 1. These are all positive quantities. So you look at that, summation Ex minus 1 is actually a positive quantity. So whatever is the genus, the other genus has to be bigger than or equal to this. So it really says, kind of, it forces some condition. When I have a Y, what surfaces can map onto this, it gives a very strong conditions. Some consequences, since the genus and degree ramifications are all non-negative integers, these are the following easy consequences. If X has genus 0, which is same thing as saying it's a sphere, S2. Okay? Then F must have ramifications. Okay? And if X has genus 1, so the first one says that P1 is simply connected. Because any map, there is no covering for P1. But these are all simple combinatorial conditions from just that equation, or the Hurwitz equation. And if genus is 1, then if the genus of both are 1, then it's actually a covering. Okay? And otherwise there will be ramification. And if genus of X is strictly bigger than Y, if the genus of X actually is bigger than 1. Unless F is an automorphism. Okay? And this is what I wrote there. Ax is strictly less than given for morphism is non-constant. Okay. Now let's look at a little bit about unramified maps. Absolutely no ramification. Okay. So which means what? So what is an unramified map? Unramified map means there is no point is ramified. So ramification locus is empty. Okay. So what are the examples like kind of? So there's one trivial way to do is like you take all the ramification points and remove them. Okay. So that will map. At every point it is unramified. But this is kind of a cheating. This is not a good covering map. So to get a covering map, you need a little more. Okay. So unramified map of compact Riemann surfaces are actually topological covers. So that means every point has exactly D distinct points. And that won't happen, right? If I remove the ramification points, some fibers are actually shot down. So it won't have the same cardinality. So yesterday when Nitin said the covering is exactly D number of points. And what is next one? An inclusion map of an open, again, open subset is also unramified map. But then it's not surjective. So you can't say for every fiber. Okay? So when F is unramified, an induced map on the fundamental group is not surjective for a covering. No? Okay? So pi 1, if you have a covering map, so unramified map of compact Riemann surfaces, the induced map on the pi 1. So in the next slide, I'll talk a little bit of pi 1 also. The fundamental group and covering spaces. So there is a nice dictionary like your Galois theory. So field extensions are Galois groups. Similarly, there are this étale covers and Galois groups that has come in many talks already. Okay. So given a topological space X, choose a base point The fundamental group of X is homotopy class of groups. This is the definition in topology. Okay. So that means at every point you keep taking loops and look at up to homotopy. So that's the definition of loops. The pi1. The constant loop is identity. And then tracing the loops one to the other define the product. So in other words, you take suppose there are two loops, you go by first loop alpha and then go by second loop beta. That's alpha times beta. So that's the definition of the product. Now you need to check all these are well defined in scope, modulo, homotopy, and so on. But these are all standard changes. And a covering space is a local homeomorphism that we already said. Covering space is something where it's local homeomorphism and it's evenly covered. For every point, this should be like there is a local triviality. Okay. And because of this, there is some uniqueness about path lifting and homotopy lifting and so on. But that's exactly the reason I said if I start with a line, like a line here, it will always lift to some line there as long as the line is lying inside your unramified locus. And given an initial point, you can go. And then you can also see something more. There is a relation. So suppose the space of all this corresponds to some group, then you can see this how the pi1 is sitting inside the other pi1. As I said, it's actually sitting injectively. That's the last statement. And the index of the subgroup is exactly the degree of the group. Okay. So that again will come simple computation with path liftings. So you can give the cosets as the number of fibers. So that is a map. Okay. Now I'm changing my gear. Now I'm moving into algebraic geometry. So now I wanted to look at all this in a different perspective because after all I'm looking at maps. So how do I describe maps in algebraic geometry? First, how do I describe spaces in algebraic geometry? Or analytic geometry, or in fact any geometry. So what you usually do is you have got a space, okay, and you wanted to develop the kind of space out of it from the functions on it. Actually, the underlying philosophy of algebraic geometry is the spaces are in one-to-one correspondence with the functions on the space. So that is how you have got the space, you can take its spectrum, and given the spectrum, you can look at the functions on that to give the corresponding algebra. So the algebra and the corresponding spaces are in one-to-one correspondence. So now, what does that mean? For every point, there is a basic object. Like here, the basic object was the disk. Okay, so I can take all holomorphic functions on the disk and I can assume that is sitting on this portion. And this one, again, functions on the disk, they're sitting on this portion. And then there is a nice way to patch them, and that's called sheaves. So I will not get into the basic definitions. So by function, so there is, you must have already seen this analytic continuation. You do some analytic part here, and then analytic part there, then analytic part there. So once they patch, if they agree on this, then you get an analytic function on the union. So this is the way you go on. Okay, so that is how you get a sheaf. So, and that sheaf is called structure sheaf and usually denoted as Y's. So when you have a map from X to there is X and there is a Y. So when you have a map from X to Y, take a point, take a small neighborhood. So inside that there are neighborhoods above. Okay. On all these there are some functions, right? So they are actually kind of their algebra. There is a multiplication there, but the functions from here are actually also pulled up. So if I take a function here, then I'm getting functions here, here, here. So I'm getting a map from OY to, you don't call it OX. You don't get a map from OY to OX, but the sheaf given by the functions on X on Y. That is how this object is called, the direct image sheaf. It is like on Y, you take a point, Instead of looking at all functions, you look at all functions in the neighborhood on the pullback on X. Okay. So now the idea again. So this is again, and this is an algebra. So this is a sheaf of algebra. So the sheaf of algebra should drive something about the geometry of the map. That's really the idea. So we need to give this ramification or genuine ramification, which I'm going to define, purely in terms of algebra 2. So we will give that too. Okay. Yeah, so some property of this structure sheaves, what are they? So given a Riemann surface X, we consider the sheaf of functions obtained by associating to each open set the set of algebra functions and denoted by the sheaf of X. Given a map, OX is an OY algebra. That's what I said. So there is already an algebra, and OY there is a map. By taking just functions on Y and putting up, they will give function here, function here, function here. They are all functions on the whole inverse region. So that gives you a map. Okay. So that gives you the inclusion of OY inside F lower star. This actually for Riemann surfaces, this is actually locally free. What is called a vector bundle. So now I'm going further away from just the topology analysis. These are more deeper things. Okay. So then I have to use some vector bundle properties, which are going to come up now. Okay. Now there is for curves, there is a very nice criteria for etalness. Okay. That is a map of compact Riemann surfaces is unramified. If and only if, look at this sheaf of algebra, it has degree 0. So purely numerically, if it has just degree 0, it's already etal. And in fact, it also follows it is semi-stable then. Okay. So they are equivalent. F lower star rho is semi-stable, F lower star rho is degree 0, and F is etal, or F is equivalent. These three are actually equivalent statements. So that tells you what is genuinely ramified. Okay. A map X to Y of connected Riemann surfaces is called genuinely ramified if the induced map of fundamental group is surjective. Okay. The following are equivalent. I think I missed some lines here anyway. So F is genuinely ramified. The fiber product is connected. Okay, so that's purely its topology in even lower levels. And just to only look at just the connected components. So if you have the fiber product connected, that's also equivalent to genuinely ramified. The other thing is the beta subabundant. That's called, I think, we have been talking about it, harder maximum filtration of the vector bundle F lower star rho. And look at the first harder maximum destabilizing piece. That's called beta subabundant. And that because OX is OY is already sitting there, the beta subabundant has degree 0. Then you can prove that inside F lower star OX, the degree 0 part of that is actually a sheaf of subalgebras. So if you take that sheaf of subalgebras, that its spec will give you the drawing. So that's the idea. So yeah, this is the same statements again. Yeah, let me. So for some slight digression, probably I should say a little bit about the fiber products. That's at least the third case. Yeah. What is this fiber product? See, when you have a map from X to Y, for any space as X to Y, and then I can again take X to Y, the same map, I'll write it once more. So there is a reason why I write it in this way. And then you take X cross X over Y. So this is called a fiber product. What is this? This is actually a subset of the product. How is that defined? It is so let me define it. x cross x over y is nothing but set of all xy such that, or maybe x1, x2, because other one is y. I don't want to get confused with points. So x1, x2 such that fx1 is equal to fx2. That's it. So it is set of all points that one come from here, one come from there. They should be the same point on y. I used to say fiber product is nothing but product of fibers. Because if I take a point here, the fiber of this is precisely the fiber on this cross the fiber on that. See, usually this word doesn't commute. So the fiber product is nothing but the product of fibers. And it's actually true. So now let us look at the special case of Riemann surfaces. It's a local condition now. To analyze the local structure of x cross y, x over y, I just need to understand the local map. Okay. So suppose this map. So suppose these are Riemann surfaces. Suppose this first map is like z goes to z power m. Let's say this is zn. And this map goes to z power m. So that means, after all, on same y, I am going to look at 2 points above. I'm going to look at the behavior because I want the points have fx equal to fx1 equal to fx2. 2 points above, and then how this product inside. So it's actually the product of the two disks, how that is looking like. So it is given by fx1 equal to fx2. But fx is given by z goes to z power m. And the fx2 is given by z goes to z power m. That means they are equal, means I am looking at z1, z2 such that z1 power m is equal to z2 power n. Or maybe the other way. This is m. Or another way to say it, this is equal to 0. This is the space. So I'm looking at two variables, z1, z2, complex variables, and looking at this, solving the equation, z power n minus z power m is equal to 0. Now, if one of them is 1, suppose m is 1, then this will look, or n is 1, then this will look at z1 minus z2 to the power m. So the first order term is non-zero. So this is something smooth. Yes? So the moment one of them is 1, okay, and the other one is anything, it's just a one smooth component. Yes? Suppose m equal to n. If m equal to n, then what happens is zn minus z1n minus z2n is nothing but z1 minus omega z2 whole power n. No, sorry, not whole power, product. Omega I, where omega i's are nth root of n. So there are exactly n smooth components. Okay. So that is how. So when the ramifications are same, then they will split into smooth components as many as the d, or as many as the ramification number. Now suppose there is a GCD. Suppose this is an n and this is r times n. Then again you can put a z to r inside this and then you can write. So it will be like z minus. So it is if n and r times n, it is a multiple. If the GCD, now I will take out the GCD part. Okay, so this is going to be again. So if one of them divides the other, then it's again smooth components with how many number? As many as n. So that's the smaller the dividing number. Okay. So something like co-prime. So z square minus z2. This is a genuine plus. So if it doesn't divide, so you take the co-prime part. So take the GCD out and look at the co-prime part. So co-prime part will look like a genuine plus singular and as many number as the GCD. So a local picture of the fiber product, at least in the case of curves, is very explicitly understood just by knowing the ramification indices. Okay. So locally is okay, but now what happens globally? That is this. That is the second condition. Genuine ramification says globally it must be connected. So after all, ramification, genuine ramification must be some global fact. And the global fact says it's connected. Okay, so that explains. And in fact, all these things make sense in any characteristic. Fiber products make sense. And so some main observations to look at these equivalences are like, first look at that, take the direct image sheaf, pull it up, and then you will see OX is already there because when I push down, the OY is there. So when I pull back, OX will be there. Okay. Go modulo the OX. This is a vector bundle contained in direct sums of negative line bundles. Yeah, so I think some lines I filled it up, that's all you see. So maybe it was not saved. Should be of same rank. In other words, it's contained in direct sum of negative line bundles with torsion quotient. Okay. So that line is missing there. And here also, actually to do that one, main point is to use the connectivity of the graph. So it's a bit tricky, and it took some time for us to properly write the proof of that part. And the consequence of that is actually what we have written as the 2. So for instance, when W is semi-stable, I don't have to write max. So it really says if I take F over star O, and in fact I have to go modulo the O. So this is less than or equal to. In fact, there is a stronger one. That's what I have written later. That the mu max of this F over star OX mod OX is actually strictly less than mu max of W. And this is very important to understand how the pullbacks of bundles behave. Yeah. Now it gets more tricky when you go to higher dimension. Okay. So let X to Y be a finite separable. 10 minutes. How much? Yeah, more, 15 minutes. Okay. That's, anyway, I don't have many more. Yeah. So I'll essentially only state the results. Yeah, so you take a finite separable surjective morphism between irreducible normal projective varieties, okay, or an algebraically closed field. Then the following are equivalent. One is F is genuinely ramified. Here I take the definition as pi 1 eighth surjective. Okay, so that's my definition of and then so that's essentially the second part. Pi 1 eighth surjective exactly means 2. That there is no non-trivial étale covering from Y to Y, Y prime to Y, satisfying the condition factors to X. Okay? So X to Y doesn't factor through an étale cover of Y. That's what étale fundamental group surjective exactly means. Third is the fiber product connected. Again, even in higher dimension, even for normal case, it relates with the connectivity of the fiber product. The last one. So you take the F over star O and pull back. The point is F over star O need not be a bundle anymore. So there will be genuinely sheaves, and when I pull back, it can pick up torsion. So I have to go more the torsion. Okay? This has exactly one section. In fact, the 3 and 4 are more or less equivalent. If I just say pull back, this thing has one section because the torsion will always give some sections in general. So you have to really go more torsion and then demand for the O is only one. That's what it means. So all the rest have negative. So it's not really muse. That is the problem. So you have to be much more subtle on that part. So one of the theorems in higher dimension was to prove this canonical sheaf exists. So start with the reflexive torsion-free sheaf. Then there is a unique maximal locally free subsheaf of same slope. That same slope is the line is missing. I mean, of course, you can find locally free subsheaves. some very low mu's. Quite interesting. But that's not the point. Of the same mu. So this comes, so let me explain why, what was the issue for this, okay? Why we had these troubles to do the normal case. See, there is a finite group that acts on, so at least open we can say, at least we all know. You take the C2 and look at a finite group acting. And you can extend it to P2 also. Okay? So P2 and P2 mod G also you can try. Okay? So these ones, what happens is this is a quotient singularity. So when I push it down, this is actually a covering outside the origin. This phenomena does not happen if the base space is smooth. This happens, the base space is kind of badly, like just a normal variety, such thing happen. So that is exactly why. So this is what we began. You look at F lower star Yx and look at degree 0. For any sheaf also I can talk about the degree 0 part of the F lower star O. But that may not give an étal covering. Exactly here. See here, if I take that on P2 mod, what will happen is that everything will have degree 0 because on a big open set it's actually acting kind of freely. So it is a genuine covering. So once it's a covering of a big open set, so the degree doesn't change. The degree of a sheaf is determined on big open sets, on any variety. So the degree 0 is everything, but that's not giving the étal cover. So what characterizes étal cover is, if there is an étal cover, the pi over star rho is a vector bundle. So what really says is that there is no other pi. So like in the previous slide, as I said, it doesn't factor through. So if there is a pi that was factoring through a OY prime, this will be a locally free sheaf, and we are saying that this cannot sit inside. So first I have to prove there is such a unique object exists. In the beginning I thought it might even do it for any torsion free sheaf, and we realized just taking a torsion free sheaf does not work. So we really need to take a reflexive sheaf to do it. And F lower star O's are of course, O is reflexive, the direct image is reflexive. So one has to use, so it's a bit non-trivial result to prove the existence of such a sheaf and how to use that to characterize the genuine ramification in higher dimensions, especially when you move into normal varieties. For a smooth, again, this is no problem. But we have used this with the biology when the base was smooth. But there the point is, F lower star or degree 0 actually determines the étal covers, because there is a purity. Ramification must be divisors. While in general, between normal varieties, there is no purity. So the ramification could be higher co-dimension. That is why we are calling it genuinely ramified. So there are ramifications even on lower, much higher depth, probably even just at a point. But that also gets detected by looking at the maximal locally free subsheaf of the reflexive sheaf F lower star O. So that is how one translates the genuine ramification for sheaves. Okay. And then another theorem we proved was with Vishwas was genuinely ramified map of V, stable vector bundles, pull back to stable vector bundles. And when E is a pullback from the mu max assumption, we need, so this last one is actually a descent criteria. This is something of interest. So usually the only descent criteria are well known are like Galois descent. So they use the uniqueness and the group actions. So here we are saying just purely in terms of bundles alone. You take the direct image and look at certain beta subbundle and look at its rank. Okay. Beta subbundle should be of that. That's why I said mu max of F lower star E equal to mu or V. So usually the beta subbundle, sometimes even direct image is actually stable, but they all will be much lower than me. So here I am asking the mu max must be equal. So the expected degree beta should exist. That's why I didn't call beta. Because if I call beta, that could be much lower degree or lower slope. So I want the same slope. and that is non-empty is what it means. So if the same slope means there is one way back. And the moment it's non-trivial, then one can prove that the pullback of that must be that I begin with. So this gives a criteria for descent. And it's very useful in the sense that, especially after Nitin's work and so on, you might be able to handle a huge amount of bundle in one stroke. Okay? And then suppose I knew some property for a general bundle, like finite bundles. Let's say some assumption on étale fundamental group, and that will push it to many other bundles. So there is a big set of bundle, it will give a descent data in one stroke without any other, and you have no idea about the gamma or anything. But just because of this descent criteria, because there is a relative order maximum filtration and the generic thing will have some properties and so on. So it's a very useful lemma. And in higher dimensions, yeah, again, this was so this is another way of looking at things. So we reinterpreted as genuine ramification as pullback bundles being stable. So in fact, we gave a characterization saying that that was the previous slide. So a semi-stable, E is a semi-stable bundle and E is a pullback. Okay. Oh no, sorry. This is again. So this is semi-stable is wrong. So I think my correction is not done. This has to be pseudo-stable. Okay. For higher rank, we need pseudo-stability, that is extension by bundle. Or in our paper, we called it, in the biology paper, we called it LF graded. And later they also called it pseudo-stable. So the second general bundle criteria is for pseudo-stables. So where is that? Have dimension 1 theorem? Yeah, here. The IMR in recent paper. That says a map is genuinely ramified if and only if every stable bundle pullback is stable bundle. Now, every stable bundle. So it's not degree 0 or not nothing special. Every stable bundle has to pull back to stable. So first we proved that genuinely ramified to this term. Then we said, okay, now maybe if it is not genuinely ramified, you produced actual examples saying that there are stable bundles which don't pull back to stable. That essentially you just have to do it for étale powers. So we produce that. And the same results is extended in higher dimensions. Okay, so at least we are able to prove that every stable bundle will pull back to stable bundles. Yeah, there was just one slide I wrote here. I think with that I will stop. I'll make the statement. So in the curve case, so let's just go back. The main observation was that one, okay, that you take F lower star OX mod OX. It's a vector bundle contained in the direct sum of negative degree line bundles with the same rank. So with the quotient is torsion. Okay. Now in higher dimension, this is false. So for instance, here itself, there is a degree 0, and then when I go back, it's again degree 0. So that won't be contained in the negative line bundles. But what happens is, when I pull back in this case, so and go more torsion, they all will vanish at the origin. So the point is, replace the negative. See, for a curve, if it vanishes at a point, it's already a negative degree line bundle. Because torsion-free sheaves are free, locally free, which is not true in higher dimension. So in higher dimension, what we can change this first line by, it's contained in the direct sum of proper ideal sheaves. Okay. Once you have that, then you can prove you can't have morphism. So there are essentially about morphism statements. So the point is they are contained in direct sum of ideal sheaves of same rank. Okay. And with the torsion quotient. So that is the main observation there. To do it in high dimension. And with that, I'm done.
You. Any question?
Idealism, generic idealism.
See, these sheaves are coming as, see what happens is, It's essentially about vanishing at some points. So how do I, so I'll tell you something. It's a small trick. It's better to do the understanding of the fiber product. So you take this x to y and x to y, x cross x to y. So let's just look at the curve case for the time being. Then we'll look at x cross x over y tilde, the normalization. Okay. So this normalization, because it's normalization, what you will see that, so let's assume this is Galois for the time being. Then it will say that this is exactly as many copies as the degree. So this is like this. Though here there are even bad ones and then there are intersections and the fiber product might look very bad. But the normalization is always like this. And these have the same rank, but the number of components are same. Generically it's theta. Okay. So let's put some names. So let's call this nu and this is pi. Okay. Now this is f. So what is, you look at what is f lower star Ox, f upper star. F lower star Ox, f upper star. But that same thing as you pull back the O to the fiber product and push it down. So that same thing as pi lower star of O x cross x over y. Okay. But this will canonically sit inside. So pi composite nu. Pi composite nu lower star of, or nu composite pi. Lower star of O x cross x over y tilde. This is actually Ox direction B. So this is how this bundle actually is going to sit inside that. Now there is an O factor. You kill that O factor. The rest of it, we have to do very clever kind of trivialization. So you keep changing the trivialization of the O in such a way that this subbundle mod O, they all project into each of the O factors with vanishing at a point. So suppose I have a subsheaf. Suppose I have a trivial Ox to some R and a subsheaf F. Suppose the projection to each of them lands inside some Li. Okay? Then the totality will sit inside the direction. Okay? So even if it is some smaller one, this may surject. So we have to be careful about making sure the projections are vanishing at point. This is where, so while doing this is where we use the fiber product being connected. So for instance, if I have, suppose every element X has a fixed point, let's say. So then look at the diagonal component. So every other component is going to meet that. So then you look at the sigma minus, so O minus sigma or something. So you just change the trivialization a little bit and on each of the predictions. So you'll see that each of them will vanish at some point. So now suppose all sigmas may not have a fixed point. Then I have to look at all those which has fixed point, then pick up one, and then where it doesn't have a fixed point, but intersects with one with fixed point. So you have to just keep expanding your graph of the fiber product. And then the connectivity tell me that this exists. And this process can be done in any dimension. That's again.
Any other questions? Let's thank the speaker for the great talk. We'll have 5 minutes break and then resume after that.
Pullback will be always semi-stable.
No, pullback will be semi-stable. Stability. Stable pullback, stability. See, for instance, if I take a finite map, a finite content will go to trivial map. Because it's separable maps. So pullback is semi-stable is all. I think stability is also.
That happened when it is genuine.
No. It can only if in the sense that if every bundle pullback is stable pullback is stable, then it's stable. But some of them may still pull back. Stable. It goes inside it and some of it. That controls some homomorphisms, some origins. Yeah, semi-stable pullback to semi-stable is well known because you can do Evahori descendants. But
That always happens.
that always. Stable pullback to stable.
If and only
You're saying that's important. I don't know how much of
that. Can you hear us? Hi, yeah, so we'll start after 5 minutes. Maybe you can share your slides and we can set it up.
Okay. Okay, so I'll just share the slides on screen.
Yeah.
Okay.
Okay, great. Yeah, we can see it.
Okay, thank you.
Well, For the second talk, we're pleased to have Professor Moina Kothar, who will tell us about equivalent splitting of two principal bundles over projective spaces.
Hello, thank you. And thanks to the organizers for the invitation. It's kind of unfortunate that I had to cancel my trip to SRM. I hope I'm audible. Yeah, okay. So yeah, so thanks. And so I'm going to talk about some results on toric principal bundles. With Arijit Dey and Indranil Biswas, I have been working on this for quite a while. And recently with, contributions from Jyoti Dashgupta and Vibhash Khan, we have managed to prove some of the results that we have been aiming for kind of a long period. So let us first, so the toric principal bundles are principal bundles over toric varieties, which are equivariant with respect to the torus action. But let me first just briefly say what a toric variety is. So one can think of a toric variety as a partial compactification. So all my varieties are defined over C. And so you look at the complex algebraic torus of fixed dimensions, say C star to the n, and you can think of a toric variety as a partial compactification or a compactification of this algebraic torus. Now, a better way to say this is, this compactification has to be equivariant. So a better way of saying this, a variety X endowed with an action of an algebraic torus T of the same dimension. And you also want X to have an open or dense T orbit. And for this talk, we'll assume that this our toric variety is complete. In other words, is compact, and also that it is non-singular. And typical example would be the projective space. And now such a toric variety would be the union of some affine varieties which are stable under the T action. And these actually we can we'll have like a finitely many of these. And these affine pieces, for example, Pn, you can write it as union of n plus 1 copies of Cn. So in the same spirit. And these affine pieces of X will denote by X sigma. And because our variety is non-singular, each X sigma is isomorphic to Cn. And actually the torus action on X sigma would differ from the standard action of torus on Cn by some automorphism of the torus. So it would be standard up to some automorphism of the torus. Now, each X sigma contains a unique torus fixed point, just like Cn, the origin is fixed. So exactly, so this is basically because I'm assuming complete and non-singular. I have these simplified assumptions. And so this a torus fixed point I will denote by little x sub sigma. And I'm denoting this collection of, these affine pieces, each of which contains a torus fixed point by capital sigma star. Okay, so and I'm saying that this capital sigma star, you can, as a set, you can identify with a set of torus fixed points of X. Okay, and there is also natural identification of the open dense orbit, which we may denote by O with the torus, and the identity element of T under this natural identification will be denoted by X sub 0, so point in the open dense orbit. So this will play like a very important role. So given some bundle, we are going to focus on the fiber over this point x0, and because of the torus section will be free on this open orbit, right? And sort of then if the bundle has a torus section, then sort of it will transport this fiber over x0 around in O, and many objects of interest to us would kind of be generated from that fiber over x0. All right, so I'm jumping the gun. So let us say first what's a toric principal bundle. So let G be a linear algebraic group. Let pi from some variety EG to X be a principal G bundle. So that means that, by definition is that this is locally trivial in Étale topology, and so locally isomorphic to open subset of X product with G, and so but in Étale topology, what we'll see is that in our case we can replace Étale topology by Zariski topology. So we'll give this argument for this local trivialization in a little while. So as this sort of standard convention, we assume that so G is acting on this variety EG on the right. This action is free, and we use the notation little e as an element of EG, and this right action we denote by little e dot G, little g, where G is an element of the group G. So please stop me if there are any questions. Now, so this I just described sort of like a principal G bundle. Now, X in our case is a toric variety, comes equipped with the torus section. Now we say that this principal bundle EG is a toric or T equivariant principal bundle if EG is endowed with the lift of the torus section on X, and the torus section on EG commutes with the torus with the G action on EG. So we think of the torus acting from the left and the group G acting from the right. Okay, so here is the result that I was talking about, that trivialization over Zariski open sets for such EGs. So for EGs, for torus equivariant principal bundles, we have such trivialization over the affine toric pieces of X. So here EG restricted to X sigma, that would be equivariantly, torus equivariantly isomorphic to X sigma cross G, where the T action on X sigma cross G is given by a homomorphism of the torus to G. So that will denote by rho sigma. And actually, this homomorphism is easy to identify. You have the fixed point little x sigma that's fixed by the torus, and you look at the fiber of EG over that fixed point, and you have a torus action on that fiber, and from there you can determine such a homomorphism. It's not unique. You have to fix some base point in the fiber, and that will determine actually rho sigma up to conjugation. So if you change your base point by some element H of the group, then there's a conjugation by H for this homomorphism rho sigma. Okay, so but so here it is like how this product torus element acts on the product, T acting on X comma G is Tx. So that's the natural action on the base, and this rho sigma T dot G. Okay, so this trivialization result, one can obtain it quite generally in every characteristic by using what is called Luna's slice theorem, and its generalization to positive characteristics by Beardsley and Richardson. And in the complex case, the result has a slight, more general version. So in the complex field case, let me just, you can have a reductive group, not just a torus, acting on a normal affine variety, which is topologically contractible, but with a dense orbit. And so basically replace the group acting on the base, this torus, by, you can replace it by a general group with some restriction on the action, like dense orbit. And actually it's known that if the orbit has, the maximal orbit has, I think, codimension 1 or higher, then such a trivialization, equivariant trivialization does not exist always. So there are counterexamples due to Jerry Shores. Okay, so we wanted to classify all these torus equivariant principal bundles. And for vector bundles, torus equivariant vector bundles, there are two main classifications due to Kaneyama and Kliachko, both from roughly the 80s. And so we have sort of generalized both of these approaches. And today, in this talk, I'm focusing mostly on the approach of Kaneyama. And so let's stick to that. So anyway, some of these ideas also appear in Klyachko's classification, but he of vector bundles, yeah, but so one of the key things key roles is played by these homomorphisms, rho sigma, which sort of appear in both Kanyama and Klyachko's works in the vector bundle case. Now, I want to sort of, from the trivialization, you can see that, there exists some, using that trivialization, and if you use like a constant section of the trivialization, you get some special kinds of sections, local sections of EG over X sigma. So this EG restrict to X sigma, I will just, for simplicity, denote by E sigma. And so this sections has this property that, like T action on S sigma of X is S sigma Tx, S sigma evaluated at Tx. And the difference is given by this rho sigma T. So it tells how this sort of sections grow. So if you think, imagine of X being just X naught, and use this, and also on the open orbit, this rho sigma T will tell you how these sections grow or decay. For example, if you go to the boundary of the torus, whether the sections could be extended or not, it would depend on sort of these rho sigma T's. All right, and so now, okay, so here is just a definition of these special sections. We are calling them distinguished sections. And this condition, I mean, in general, if you just take any section, you can write TSX is S at TX times some element of the group that depends on X and T. And one can show that, being distinguished is equivalent to this function, G-valued function, rho X comma T being independent of X. And this is something that we use sometimes in the proof later on. So now one easy observation is that if I translate a distinguished section by an element of the group G, then that is also distinguished. And as I remarked earlier, you have a conjugation for this homomorphism. And right, so there's here I wrote down sort of the explanation of this conjugation. Now, okay, so here, yeah. So this fact that rho sigma is actually determined by the action of T on the fiber X sigma at X sigma is of great advantage to us when we try to classify all the distinguished sections. So our strategy now is like we have this nice kind of sections over the affine pieces, and I can study the transition to understand the bundle. I can look at the transition between such sections. But to classify this bundle subisomorphism, I should know what are all the distinguished sections so that I can see what happens if I use, if I change my collection of distinguished sections. So here is, how, what happens. So Now, there are two pictures anyway. So here is like the general case where, I have two distinguished sections, and I'll focus on how they differ at the fixed point of t, which is x sigma, and how they differ at the point in the open orbit x naught, like that corresponds to the identity of the torus. So they can differ by elements of G. We call this alpha sigma and beta sigma, and they will have possibly different homomorphisms associated to them, rho sigma and rho sigma prime. And right away we know that rho sigma prime is, sorry, here is a typo. So rho sigma prime is a conjugation of rho sigma by this alpha sigma. Okay, it does not depend on beta sigma at all. Okay, this rho sigma prime. And so this gives us some leverage. And then now the result is that, then one can, if these are both distinguished, one can check that, one can compare them sort of, because I know how both these sections, so if I consider their values at x naught, and I know how they grow because of the t action, right? They grow according to this rho sigma and rho sigma prime. And I also know how rho sigma and rho sigma prime are related to one another. So using all this, I can deduce the following, that this function rho sigma t alpha sigma beta sigma inverse, so then rho sigma t inverse, this function has to extend over. So this as such is a function, it's defined on the torus. You see rho sigma t, which is defined on the torus, is a homomorphism from torus. But for essentially the argument is, okay, you try to express, say, S sigma prime in terms of S sigma, and you come up with this expression, and it must also be defined at the boundary of the torus, because S sigma prime has to be defined over the entire X sigma. So from there, you see that this function has to extend over the entire, from the torus to the entire affine variety. And this is more or less, this condition kind of, if you can find such alpha and beta sigma, and if you have one distinguished section, you can produce the others. So this classifies all distinguished sections. And this leads, once you understand that, after some labor, you get the classification of all isomorphism classes. And so here, this is in terms of the transitions. So if I have two of these cones, say X sigma and X tau, capital X sigma, X tau, and there are these, their fixed points are corresponding small letter X sigma, X tau. I'm looking at a distinguished section from each open, affine piece, and the difference at X naught is called T tau sigma, an element of G. And then I have this kind of data, all the homomorphisms and all these differences at X naught for all pairs of cones. For all pairs of, I use the word cones, but affine pieces. And so this is now this collections, of course, I mean, if it has to define a bundle, this rho tau sigma should satisfy a cocycle condition, and that is what's written here. And the other thing is that, you know, the transition maps are just this rho tau, p tau sigma, rho sigma inverse. So the transition maps, that's natural, because if I know the value at x0, I know how the sections change basically as t varies through these homomorphisms. And so again, the transition functions have to extend over the entire intersection of the two affine pieces. It should not be just defined on the torus. So that's a condition. And so, but anyways, if you have any such collection of homomorphisms and elements of G that satisfy these conditions, you can construct a principal G bundle. And okay, and now there is also, of course, when are two such collections giving you isomorphic bundles, and so there is some equivalence. And so that I have two collections indexed by 1 and 2, and I have this, you know, the homomorphisms rho sigma 2 should be conjugates of these rho sigma 1s by some elements alpha sigmas, and the elements, the differences, you know, they are also related in a natural way. This second equation here. And also we need this extension condition just to make sure that, you know, you are using some distinguished section. That condition, the extension of this, you know, thing involving beta sigma, alpha sigma inverse, that extension condition is just a check that you are using distinguished section and not something arbitrary. So basically, you know, this describes all the this data, equivalence classes of this data. So these three conditions are describe the equivalence, and you have isomorphism classes from these equivalence classes of data. Now, with this approach, we were able to compute some equivariant automorphism groups of the principal bundles, first of all. And so here again, the philosophy is look at x0, and torus equivariant automorphism of EG will be determined by, if you choose a base point in the fiber over x0, you look at this automorphism phi, and it's given by E dot G from some G. And so suppose you fix E and work with that. And so this gives you a injection of the automorphism group of the EG into G. So it's a subgroup of G, and I need some you know, condition. So basically, the idea is that, you know, once you have at a particular point E, you know what happens, then by G equivariance, you know, on the whole fiber. And by T equivariance, you know what happens on the dense orbit, just starting from the fiber at x0. And then you can apply some continuity principle to know what happens in the boundaries. So basically it's determined by what happens at the point, at one point E. And so anyway, so I have to show you some, we have to deduce some, so this is what I was explaining more or less. And now we have to deduce some condition, again, in terms of these distinguished sections. So suppose you have such an automorphism phi, and you take a distinguished section as sigma, and you define this function psi sigma, g valued, by phi of s sigma x. So you are defining this function on this affine base where you have a distinguished section. And now phi of s sigma x lies in the same fiber, in the fiber over x, right? And so it differs from s sigma x by some element psi sigma, which again depends on x, psi sigma x of g. Now I want to give a condition on this. I mean, I just want to study this and come up with some condition on the element g actually. Like, can I have an arbitrary g? That's the question. And what I do is, okay, so now put x equal to x naught in this defining equation over here. And then you apply t on both sides. And so now by definition, I mean, this t action commutes with g action. So you can take on the right side, I'm looking at t inside. I mean, t acting on s sigma x naught. And here, next step, by definition of rho sigma, I'll write this as s sigma t x naught dot rho sigma t. And on the left, I'll kind of do the same. And because the phi is t equivariant, I can bring t inside, and I'll do the same on the left-hand side. And so I write it similarly, and so on. And because phi is g equivariant, I can bring the rho sigma t out, and then I can take it to the other side, I hope. At some point I take it. Now, okay, now I'm just simplifying this, and yes, so, okay. Now, here this phi, by definition of psi sigma, this is phi of s sigma tx naught is x sigma tx naught dot psi sigma at tx naught. And now I am ready to say that, now psi sigma tx naught is s sigma I can sort of forget from both sides. And I have psi sigma tx naught is rho sigma t g rho sigma t inverse. And as this psi sigma extends to the whole x sigma from the torus is identified with open orbit, which is inside x sigma. So, right, so again, I have this extension condition that this function rho sigma t g rho sigma t inverse extends over x sigma. And okay, so not all g's may be permitted, but any g in center of g would be fine, right? Then this rho sigma t's would cancel out. So now we define this group A sigma. This is all g little g's in g such that this extension condition holds. So this is like the automorphism group of the bundle restricted to x sigma. And if I intersect all these A sigmas, I get the automorphism group of the torus. And as I said, this center of G is in the automorphism group, but it's not hard to construct examples where the automorphism group is actually bigger than the center. And for example, if I take Pn cross product of two projective spaces. Then I can look at the tangent frame bundle and I can compute explicitly and show that. And these kinds of automorphism groups, one can, these frame bundles of tangent bundle, these examples can be dealt with using Kliatchko classification, essentially because they're so closely related to the tangent bundle. However, if I do some extension of structure group, then one can show that we can also compute some of these automorphism groups. And actually, we computed some extension of, I think GL SL2 in, so sort of I forget exactly, but the embedding of SL2 in GL3, that embed using the determinant. So using such an extension, we can compute for such extensions also these automorphisms, starting from the frame bundle. And those, actually the automorphism group increases in size after the extension. And this is something that one cannot compute using Kliatchko's vector bundle methods. So using the automorphism, we also have, we can also deal with we have some interesting result on reduction of structure group. And so here's like the standard definition of reduction of structure group, that there is a subgroup H, and you have the, this extension, and suppose you have EG can be made isomorphic to the extension of EH, where H is a subgroup of G, so extension of EH by G. And so in other words, intuitively, all the transition maps can be sort of put in H, basically up to some, up to like, in our case, use of up to some certain choice of distinguished sections. If you can change your transition maps and make them lie in H. So now, okay, so we have, so we have a condition in terms of our data for such an extension, for such a reduction. So I'll just read through that. You have alpha sigmas and beta sigmas to give you, these distinguished sections, for instance. And, these alpha sigmas, okay, so these new homomorphisms have got to be in H. These conjugations by alpha sigmas. These changes in the over X naught, the differences in distinguished sections at X naught have to be in H. And this extension condition here, H is not involved, but it's just that make sure that you're using distinguished sections. Okay, so now, so that was sort of natural. Now, we have an application to reduction to Levy subgroups. So let me just recall that, if G is a reductive group, then a subgroup H of G is said to be Levy if H is the centralizer of a torus in G. And for GLN, we have this kind of block diagonal forms for Levy subgroups. Now here is our result says that if EG admits T equivariant reduction to a Levy subgroup H if and only if the center of H, or specifically the identity component of the center of H, is contained in the automorphism group of EG. Okay, so this is somehow, I'm connecting the automorphisms with this reduction. Okay, so one direction is easy. So center of H is of course in automorphism of EH, and there is a natural inclusion of the automorphism of EH into automorphism of the extension. Okay, so which is EG, the extension is EG because I'm assuming reduction. Now the other way works as follows. It's slightly, one has to be slightly careful with this side. Let K sigma be a maximal torus of G containing the image of the homomorphism rho sigma. And so you see the automorphism, local automorphism A sigma is again, this elements of G that satisfy this extension condition. And now if you take a torus that contains rho sigma, those elements will commute with rho sigma. So this torus, the elements of this torus K sigma will satisfy this extension condition. So K sigma would be inside this A sigma. Okay, I'll just neglect these identity components. Okay, now you take a maximal torus of, so this has, the first statement had nothing to do with center of H. Now you take a maximal torus of A sigma. Now here you are using the assumption that, center of H is in automorphism of EG. Now automorphism in EG is intersection of these A sigmas. And so this, right. So this center of H would be in A sigma. And now consider a maximal torus. Center of H is a torus, and you consider a maximal torus containing this center. You call it K sigma prime. And so now you have two maximal tori in A sigma. So they are conjugate by some alpha sigma. And this alpha sigma is crucially, it's the alpha sigma is coming from A sigma. That's what we need. And okay, so that tells me that rho sigma is an element of rho sigma T is an element of K sigma. So this alpha sigma inverse rho sigma alpha sigma is in K sigma prime, and K sigma prime is contained in, so K sigma prime contains the center of H, and so it's in the center, it's a torus, so it's in the centralizer of the center of H, and by as H is Levy, this centralizer is H. So this alpha sigma inverse rho sigma T alpha sigma is in H. And this is like, in our, if we go back to our last result, for reduction, I needed to find such an alpha sigma, okay? And now for beta sigma, I will just put identity. Okay, so for beta sigma, I will just put identity. And then you have this condition involving alpha sigma inverse beta sigma. whatever. So I'll show you that thing again. Yeah, Betas rho, this extension condition. And now you notice that as alpha sigma, so you have this rho sigma t, alpha sigma inverse, rho sigma inverse should extend. But this is exactly the type of thing, the condition that elements of a sigma satisfy. So, okay, so, you know, and because alpha sigma is from a sigma, you have this condition is satisfied, and you have produced, using these alpha sigmas, you have produced a reduction of equivariant reduction of structure group. Okay, so may I know how much time I have left? Hello?
Yes, you have at least 12 minutes. 12
Okay, okay. So thank you. So now we can use this to look at equivariant reduction to torus, which is called splitting. So I'll specialize and try to look at splittings. So so when can I reduce the structure group to a torus? So we need one more lemma, which is, so suppose you have an injective homomorphism of G into G prime called phi, and you assume that both G and G prime are reductive, and let E phi be the associated extension of EG. Then okay, so now the lemma says that E phi admits equivariant splitting implies, so if this extension admits an equivariant splitting, then EG admits equivariant splitting. Now, there is a reason we are trying to get this kind of lemma. Basically, what we'll be trying to do later is put G in some GL and use results, splitting results for vector bundles. And with this lemma, I can kind of obtain splitting results for G bundles. So now to get this lemma, maybe I'll be kind of, yeah, I mean, this is probably the last lemma where I try to explain the steps a little bit. So define a sigma prime. So I have, you take the images of these rho sigmas, and so rho sigma composed with phi, you get into G prime. And then like our earlier condition for automorphisms, we take all these G primes in G prime such that these conjugations extend over X sigma. Now here is some kind of claim, which is, it takes a little bit of work to show. I mean, it's, yeah, anyways, so the set theoretic inverse image of A sigma prime is then actually equal to A sigma. And yeah, I don't exactly remember the proof, so, but it's not fully trivial. And the claim implies that, and if I take the inverse image of the automorphism group of E phi that equals the automorphism group of EG. Okay, and now using that we can prove, again, there is some argument. So we want to prove that, you know, if E phi admits splitting, then EG admits splitting. So let cannot be a maximal torus of G, and phi k not prime be a maximal torus of G prime that contains the image of k naught. Now, if phi admits equivariant splitting, so if phi, that means if phi, you know, without loss of generality, I mean, if phi admits equivariant reduction to some torus and without loss of generality, because all tori are conjugate, I can assume if phi admits equivariant reduction to actually this k naught prime. And now I use, so because k naught prime is a maximal torus, it's Levy, so I can use my last theorem, and so of course it's also its own center. So then by my last theorem, k naught prime is contained in automorphisms of E phi. So if I scroll back and to, that was the, yeah, that result, we are using theorem 5. And we are then almost there. So yeah, and okay. And now k naught, that is, you know, because phi is injective, is just phi inverse of k naught prime. That is contained in, this is phi inverse of automorphism of E phi. That's just from this. And this, by my claim, is automorphism, phi inverse automorphism of E phi by the claim that I made earlier. This is automorphism of EG. And now again, using theorem 5, we have that in the reverse direction. We have that EG admits equivariant reduction to k naught. Okay, so EG admits a splitting. So finally, I'd like to apply this and to the following situation. So let G be a reductive group of GLRC. Okay, where R is less than N. Now, N is basically dimension of Pn here. So let EG be a T equivariant principal G bundle over Pn. So basically, you know, in vector bundle case, if you consider rank less than N, we you know, called in small rank. So it's, we're trying to get some kind of analog of that. So, okay, so with this condition, like G is a subgroup of GLR and R less than N, then EG admits T equivariant splitting. So this theorem, you know, generalizes famous theorem of Kaneyama about torus equivariant vector bundles on Pn of rank R less than N. And okay, so now the proof is very straightforward. We just have to use the fact that, I mean, use this last result. So phi, you take you know, the embedding of G in GLR, And by Kaneyama's theorem, this E phi. So basically, I mean, this vector bundle associated to E phi that splits. And from there, you can deduce that E phi itself splits equivariantly. And then by the last theorem, EG splits. Okay. So anyways, we were, we had, I mean, we had this theorem in mind for a long time, but it's sort of an anticlimax after all the proof was done. And we were looking at, the literature, and we found that this theorem, actually, if we combine some known theorems, so there's some work by Bishash and Parmo, and also there is another which I failed to forgot to mention here, another work by Bishash, Gomez and Hulla. So if those theorems, two theorems are combined, then one also gets this result, more or less in a straightforward way. So, okay, so that's all I have to say. Thank you.
Thank you. Any question?
So I would like just to make a remark that we also studied equivariant stability of the storic principal bundles, and showed that that's equivalent to stability. But Arijit is going to, I think, talk about it tomorrow.
Okay, if there are no questions, let's thank the speaker for the good talk. Thank you for
somebody lost mobile in the bus, so that our driver found one mobile. Yeah, so our can call it script. And have written some cab numbers, phone number, and autos numbers. Those are staying in the number still, they can call.
Hello.
Professor Balaji.
Yeah,
Yeah, yes.
I'm
yes.
here. So,
Yeah.
just want to share screen first and just check out whether it's all right. And another thing I want to do is I want to log in from another machine also at the same time, because if I use this notability, then you won't be able to see me. So can I log in as a co-host from something else? That's my question.
Co-host. Yeah, I think they can add.
Let me just try, because see, it's not allowing me to log in from another machine at the same time.
Yeah. Just one. Yeah, we'll get into the ID first.
Pardon? Yeah. Hello.
Hello, Balaji.
Yeah. No. See, I'm using my iPad to go. I'm going to give a talk in this.
Yeah.
In this, I'm going to use this thing called notability. Okay, where I can write. Okay, but if I do that, you won't be able to see my face. So I wanted to log in from my MacBook Air at the same time. It is not allowing me to log in there unless, I don't know, maybe you have to call me a co-host at the same time.
One minute, sir. Now, Sarat sir wants to have one link to you, sir. In the link, you can join as attendee. Then we will promote a panelist.
Sorry, I didn't get it.
Now we will share our link to you, sir. Use the link.
Yeah. You'll send me another link?
Yeah. We will send.
Yeah, okay, thank you. So here, let me try to share screen first and show whether it's working all right. Can you see my screen?
Yes.
Everything is fine?
Yeah, we can see. And also we're running a little bit late, so we'll start at maybe 11:35 or something.
No problem at all. No problem at all. Just send me the other link so that I can log in there.
Yeah, I think they're on.
Okay, thanks. Nice.
So after it, you are going outside normally, but that link has to register. Yeah, again, but also controlling, you have to register that controlling was. So one link, sir, already is joined on the page. We can't use the same link to another link. So
You have to send me another link.
Yeah, I think they're discussing it how to do it.
Yes, sir. Thing is that you have to register. The link is there.
No, I've not registered or anything.
Yeah,
you see, if I have to use my
email ID and you will get some link, and they will make you as a panelist.
I'm already a panelist here.
Already panelist on what device? For you want to connect for one more device.
So I'm not able to hear you. Sorry, can you tell me?
Yeah, if there is a registration link. If you register, you will get on Zoom link.
Okay, just a moment.
Yeah.
Let me just try that. Yeah. There's a registration link, is it?
Yeah. Then you try to join. Our IT will make you as a yeah.
Where? So there is another link that you sent me.
No. We're not going to send any link. You need to register.
Okay.
Immediately.
Okay. So you're going to send me a link now.
Okay. So the registration link you will find our conference website.
Yeah, you're going to send me the registration link now?
No. So I'm going to send it to you.
Yeah.
Okay. It is going to put that link in the chat box.
Okay. Just a moment.
Yeah, yes, the link is there. You just click on it.
It's there in the chat box, is it?
Yeah.
Just a second. How do I HTTPS? I have to type this, is it?
Yeah, click on the link and
No. If I click on the link, then no, I need to do it from another machine.
sorry.
No, I need to click on this from another machine because I want to use my MacBook Air.
Also,
So I thought you could send me an email, then I can just go and click it.
okay, we are going to
Send me an email on this.
yeah. Okay, we are going to send.
Yeah.
Hello.
Yeah.
I just sent that mail through email.
Oh, wonderful. I'll just, once I get it, I'll click there and then I'll come in.
In Gmail, right?
That's in the Gmail, yes.
Yeah.
So I click there and I have to register, is it?
Yeah, yeah. Then you will immediately get the.
Yeah, you tell me how to register. Let the mail come now.
Yeah, yeah. Yeah. It's working?
I've not still gotten my mail.
Okay.
It's still not come.
Sorry?
I haven't received the mail as yet.
So just refresh it.
Yeah, I've been trying to do that. Yeah. You sent it to me, is it?
Gmail I can say. Did you get the link?
No, I didn't get any link. I didn't get any email. See, if I click here, see, my problem is. Let me just see. Yeah, let me just go here.
One more thing is the past. You can give credential details also that.
Pardon?
Zoom credential, pass, we have an ID number and the passcode. Means that if you have that, your laptop, if it is Zoom is installed, click on the Zoom, then we can say,
I can say join, is it?
Yeah, just click join meeting, sir.
And then what do I give me the
I will tell the meeting ID 984
984
3196
3196
6509
6
509.
509. Okay, I just joined.
Yeah, it will ask for passcode.
Yeah, what is the passcode?
221
Huh?
221
221
535
come again?
535.
35. Okay, done.
So after that, redirect to your browser for registration, then you will register.
It again says unable to join the meeting. You've already joined this meeting on another device, it says.
Maybe you are logged in both mail ID, same mail ID in both devices. So
Pardon? I am logged in. See, normally when I do this talk, I use my iPad to give the talk and use the other machine to be, because this notability that I'm using does not allow the audience to see my face.
That one is actually we registered your mail ID as a panel link. So
Yeah.
at the same time you can use one mail ID in one device. So another system also you are logged in the same mail ID, you can log in. Sir. Yeah.
I see.
Take that link, same link for you.
So what do I do now? I have to go through. I have to log in from where?
So I sent that link.
I see. Let me just see.
Gmail ID. So I'm going to say forward that link.
Otherwise, it's okay. I mean, people won't see me. That's all. I mean, I can go on talking. But if they see me, it will be easier sometimes. There's no issue. So right now, am I registered?
You can see also. You just open your video. You can see as well.
I'm trying to. Your mail is still not come. Our registration open. HCL is that? No. Not this one.
No, you are suggesting same email ID. I think you will not able to do it. So because so it's better you just try to share. Please share your file, then we will see that.
Okay, fine. Yeah, I'll share my screen now, and we can.
Yeah, so I think we can see you there.
You can. Doesn't matter if you can't see me. Is my screen visible?
Yeah, we can.
Okay. Yeah. So I mean, you can hear me. You can see the screen. That's more important than seeing me.
Yeah. So it's clear.
Yeah. So I won't try to join from the other machine then.
Okay.
Yeah. See, if I can join as I can't join in two machines as a panelist is what you're trying to tell me.
Same email ID.
Same email ID. Okay. Yeah. Okay. I see. Because in other conferences I could do it. That's why I was wondering about it. Yeah. But as a co-host, if I join in here am I not also a co-host at the same time?
No, sir. Actually, meeting it is possible. It's a webinar, sir. Webinar is not possible.
I see.
Meeting is possible. Webinar panelist and is two options there. That's why.
Fine. No problem at all.
Okay.
You can tell me when I can start.
Right.
Professor Balaji?
Yeah.
share screen.
Can I share screen? Okay, fine.
Yeah.
Is my screen visible?
Yeah, we can see it.
Okay, good.
Yeah.
So can I start?
Electric,
You tell me when I can start.
Welcome back, everyone. So for our third talk of the morning session, we're pleased to have Professor Vikram Balaji, who will tell us about Untitled group schemes on higher dimension units.
Thank you very much for this invite. I'm delighted to see a wonderful conference. And I'm kind of unfortunate that I couldn't make it there for various reasons, personal primarily. Okay, so this talk is I'm invisible. I'm only heard here because there's some technical issue here. So because I'm using this thing called notability, it doesn't allow the audience to see me and see my screen at the same time. So please feel free to ask questions. The nature of this talk is somewhat different from the rest of the talks because it's more group theoretic, but I would be connecting it to things that people already know. So so I will follow the general format. I'll come to the technical aspects of the title and the abstract only towards the end of the talk. We'd like to see the more general aspects so that everybody can have some takeaway after the lecture. So we'll work with the field of complex numbers, primarily for simplicity and also the relevance here because we are doing geometry here. G, almost simply connected algebraic group. The basic examples one should always keep in mind is SLN, the symplectic group, and the orthogonal group. And of course, there are these exceptional groups which are very important to keep in mind as well for purely group theoretic reasons because they are not defined by forms on natural vector spaces, for many of the exceptional groups. So I also fix for this story a Borel subgroup, which should be thought of as the upper triangular matrices, and a maximal torus, the diagonal matrices. Later on, of course, I'll fix what is called an épinglage or a pinning, which is crucial for making some definitions. But for the moment, the torus, a Borel inside the group is fixed. L is the rank of this group G, which is the dimension of this maximal torus T. XT is the group of characters, and YT, the co-characters of one parameter subgroups. This is the standard notation. And I'll start with some terminology, but we will see many of the things that we'll see. We don't really require this unless we want to get into the math problems, but I'll fix what is called the root system, which is a subset of this co-characters here, which satisfies certain laws naturally associated to the basically what these roots are the weights for the adjoint representation. I mean, I take the maximal torus and take the adjoint representation and look at the weights for that, and they are precisely the roots. And they satisfy the so-called root system data, the definitions for that. And inside this, I have the generating set called simple roots, which I'll denote by alpha 1 up to alpha L. They are L in number, where L is the rank of the group. This data is crucial to make sense of the definitions that I'm going to talk about. Of course, there's positive roots inside this phi, which are non-negative linear combinations of these simple roots. I call the coefficients MIR just so that for any positive root I have, similarly I have negative roots here. Okay, so let's have one more notation. I mean, this is just because I'm going to use the term roots sometimes, so this is more important for that. Let A be a discrete valuation ring. And often I'll assume it to be complete, especially in the geometric situation. So for all practical purposes, I could work with K double bracket Z here. If I'm assuming it's complete, and the K is the fraction field here, so K the Laurent series. Okay, and when I have this algebraic group G, and when I talk about the K points of G, I mean morphisms from spec K, spec capital K to G. These are, if K is this field, this group is called the loop group associated to this algebraic group G. We're going to consider a class of subgroups inside this group GK. GK is just a group. I'm not giving it any topology, and it's just a group, because if I think of the algebraic group as a group functor, then this is just a usual group. Okay, but still, I can always think of, I can put G inside a GLN, and I can talk about subgroups of this. Notice that the entries inside GK are Laurent's, each Aij is like a Laurent thing in Z. And I talk about bounded subgroups, I mean that I'm actually bounding the order of poles inside my subgroup. So these are the bounded subgroups that we are going to look at. I'll give examples as we go ahead so that we keep things in mind. So if the case when G is SL2, which is the basic case, the standard examples of bounded groups, notice that A, B, C, D in my case are just formal power series in Z. So I write this as usual A, B, C, D. Of course, a matrix condition like AD minus BC, those conditions should be satisfied. So here I'm assuming that the lower triangular entry has a factor of Z in it. So this is this is an example of a bounded group, and then I can look at just the A-valued points of the group G. I'm looking at K-valued points of the group G, so I can look at the A-valued points of the group G, and this is naturally a bounded subgroup of GK, because all they are greater than or equal to 0 terms. There's no poles, and here. This is another example of a bounded group where I have Z inverse on the upper triangular entry and Z on the lower triangular entry. So this is again an example of a bounded group. If I look at G equal to SL3, then when I write A here, I'm just meaning that those entries are formal power series entries, and I have Z inverse on the top row and Z on the first column, and then the block of A is here. So this is an example of a bounded group again. Yet another bounded group, I could put instead of the first row, I could put first column, and the last row instead of the first column, just changing this. These two are, as we'll see, what they are corresponding to, and we'll be able to relate to them in a very natural way. Of course, I can look at something like this, and in this case, I look at bounded group where all the entries are from the power series in K, but last two terms have a Z factor. So when I put a Z factor here, I mean that there is no constant term on those two terms. That's what I mean by putting a Z here. That means in this particular entry, the constant term is 0. Okay, so these, this terminology standard will come later. For the moment, let's just look at these as examples of bounded groups. Of course, I can give other symplectic groups and things like that, but just to keep track of what's going on here. So what is this story that we are talking about? Bruja and Titz, completing some work of Evahori and Matsumoto and taking it to very great Grothendiekian levels, wrote a series of papers, close to 1,000 pages, from 1960s to 1987. There's an extensive study of these groups. The groups with the values, I'm looking at K, more generally, I'll look at K to be a local field, perhaps, and then one is interested in this kind of questions, how to understand these subgroups here, and there is a natural combinatorial structure called the Bruja-Titz buildings, which is also gives you the structure in a very nice way, and they have deeper applications in representation theory of periodic groups, and so on and so forth. So my main object here is to give some sort of an idea and relate it to stuff that all of us who are working in bundles and some sort of many questions related to bundle theory, which people have discussed in this conference. Some of them I'll relate to that. So let me just make a definition. I'll call as a subgroup of GK, a schematic subgroup. A schematic subgroup if there exists a smooth group scheme. I mean, see, we must remember that if I'm working with characteristic 0, which is what I assumed at the beginning as K is complex numbers, smooth group scheme is just a flat group scheme. There's a theorem of Cartier which says that over complex numbers, a group scheme will be smooth if it is non-trivial. So it's just flatness that's being assumed here. But in general, smoothness is essentially if I'm working in positive characteristic situation. So I want to also assume that my subgroup, so how do I relate to this? That means I have a group scheme. I have a group scheme over spec A. And I'm also assuming that, this is the maximal ideal point, close point here. Over the generic point, I want it to be what is called generically split. That means if I look at the generic fiber of this group scheme, it's just a product of my group that I've already fixed over the base field K. In general, I don't need to assume this. I mean, I can work with a group scheme over capital K, which need not be split like this. There are several other refined and subtler things which will involve Galois theory. But for the purposes of this talk, where I'm just giving some idea of this whole story, it's good to assume just this. And for many applications that we are thinking of, this is good enough. So these are group schemes which I'm calling generically split. That means the generic fiber is just the product of G cross K. And my group, I'm calling it schematic if there are sections of this group scheme. So that's what I mean. But that means A-valued points of this group scheme. So Bruja and Titz were interested in classifying schematic subgroups of this group GK. And that's the whole theory. I mean, there's a lot of work there. So let me just give some generally overview and then tell you what the questions that we are looking at and why. So the first natural bounded group that one is interested in this theory is what is called the Evahori subgroup. So this is, analogous to something like the Borel subgroup in this whole classification theory. So let me look at the evaluation map. If you think of A as a power series ring in one variable, then I'm putting Z equal to 0 in my group. So GA, of course, as I told you, is just entries which are formal power series. So I can when I put Z equal to 0, I get an element of G small k, where K is the residue field. Okay, so I get this evaluation map, and I have this Borel subgroup, which I have already fixed in the beginning itself. Of course, Borels are determined only up to conjugacy in G. So I fix a Borel, and I'm looking at the inverse image of this Borel, and that's what I call an Evahori subgroup of G. And a general Evahori subgroup is something which is a GK conjugate of the standard Evahori subgroup. This is what I call a standard Evahori subgroup. So let's quickly look at the standard Evahori subgroup in this example that I started with. This first one is an Evahori subgroup here, because if I put Z equal to 0, I get the upper triangular matrices here. So the fact that in the lower triangular entries, I'm having the condition that my power series does not have constant terms is all that I mean by a standard Evahori subgroup. And any Evahori subgroup, therefore, is just a conjugate of this. So we can similarly have, in this case, if I put a Z here, then this is an example of an Evahori in SL3, because if I put Z equal to 0, I land, this is precisely the inverse image of the Borel in SL3. These entries are the upper triangular entries. Notice that when I take conjugates by GK, the new Evahoris need not sit inside GA anymore. Okay. And there are these, instead of the Borel here, I could take parabolic subgroups, which people saw in Moinak Podar's lecture. Parabolic subgroups are subgroups of G's, which have like what we call the block structure, but one can just say that the G mod be the homogeneous space is a projective variety. So instead of the upper triangular entries, I could put a 0 here and look at structures like these. these are maximal parabolics, and there are other parabolic subgroups which contain this upper triangular. So I could have taken a parabolic subgroup here and taken the inverse image. So in particular, I mean, for example, I could have this one would give you a block. I mean, it will be the inverse image of a block of this kind. The inverse image of a block of this kind, basically. So I hope you understand what I'm trying to say here. So this is an example of a parabolic subgroup here, maximal parabolic. And then the inverse image of that is this. That's why I call this the standard, those which arise from the standard stories. But the important examples of parahorics, subgroups, I call a subgroup a parahoric subgroup of GK, those which contain an Evahori. So just like the parabolic subgroups contain a Borel up to conjugacy, a parahoric subgroup contains a Evahori. So the standard parahorics are examples, because if the parabolic contains the Borel, then inverse image of P will contain the inverse image of B. Therefore, they are examples of parahoric subgroups. Any questions? Okay. So the important thing is that there are many schematic subgroups which do not come as above. In fact, those are the ones which really we are interested in. So as I said, one has to fix what is called a pinning to talk about these unipotent subgroups which are there. This is just a definition, but more interest, these unipotent subgroups really constitute what I call the matrices with entries in with only in one. That means I'm looking at blocks like these. I mean, identity in the diagonal and one such block here. This is an example of a copy of the additive group inside my group. So this fixing these is what I call fixing also a pinning. Okay, here I'm looking at everything matricially, so it's visible as to what I'm doing. So a pinning not only fixes the torus, the Borel, it also fixes these so-called root homomorphisms, which also tells you associated to these roots, which are the points of the upper triangular matrices where these additive groups are getting put. So the upper triangular matrices entries are the entries for the roots in the GLN case. And you have these root groups. So I don't want to go too much into the algebraic group theory here. So these are the additive groups. The additive group is the standard copy of the field K, at least the K valued points of the additive group is just that. So this is I'm thinking of it as a group functor here. So you have these root groups inside this group G, which come as a part of what is called this data of pinning, or what's called an épinglage by Grothendieck. The picture of the épinglage is very much like what Grothendieck gives as pinning of a butterfly on a bone. And that's why he called it a pinning. So it gives you some sort of a fixed structure for doing certain things. And they are very much connected to the story of buildings that comes up here. Anyway, so this root system I've told you is this collection of roots here. And I also add 0 to it, and I call this set phi tilde. And I make a small definition here coming from Bro and Titz. It's, as they say, a function f on this root system, a real function, is called concave. If whenever ri's belong to phi tilde are such that the sum of these ri's also belong to phi tilde, then f should satisfy the condition that f of summation ri is less than or equal to summation f ri. It's just like a concavity condition. So this is just an abstract concave function. And why do I define this? As I mentioned here, there are many bounded groups which don't come from this Evahori, standard Evahori kind of picture. So what are they? So examples of concave functions which one can look at is, I call a concave function of type 1. If there exists a point, see, this, when I write AT here, I'm looking at YT tensor R. I'm just looking at, so that's a point. This is the so-called affine apartment, and there's a natural duality between, XT tensor R. So I look at the standard pairing between the XT and YT, and I have a notion of what is called R theta, which is now, because I'm working with tensor with R, it's a real number, so I can talk about the greatest integer function. and the minus of that. And this is a standard example of a concave function in this sense. So these numbers will come as we'll define them slowly. So a concave, this is an example of a concave function on the root system. There's another concave function that if you take what is called a non-empty bounded subset, this when I write AT here, I'm just looking at this vector space here, which is an Euclidean vector space of dimension L here. Xt is a z to the L, and this I'm just looking at it as a Euclidean space, and I can talk about a bounded subset here, the standard topology. And associated with this bounded subset, I can again talk about the greatest integer function of the infimum of r comma theta. So this is r comma theta, but the standard pairing of xt and yt here, and I'm looking at the thetas running over omega and looking at the minus of this. This is an example of another concave function. And of course, important thing is to note that there are concave functions which don't fit into the type 1 and type 2. These are the simpler ones. And to a concave function f, I can look at the subgroup, a subgroup of GK generated by the diagonal, the torus entries, TA, and the root entries which have z to the power fr here. So you see this fr are like the root entries that I did here. I mean, if you look at the what I put here, I mean, the diagonal entries are all A here. So this is the diagonal part, this is the TA. And at all the positive and negative roots that we are looking at, I'm allowing certain powers of Z. And those powers of Z are controlled by this concave function that I've started with. That's all that I'm trying to tell you. So this is a definition of a bounded group defined by a concave function. That means I'm looking at the order of poles and zeros controlled by this concave functions at the entries defined by those R's. So FR can be 0 in many places, as we have seen the examples. But at the root entries where it's non-zero, it is telling us what is the order of zeros and what is the order of poles that I'm allowing for my entries. So that's what this subgroup is. And this is an example of a bounded subgroup because I'm actually telling you what are the precise entries here. So if f is of type 1, in the sense that it comes from a point of this so-called affine apartment, then this bounded group is called a parahoric groups. These are all parahoric groups. The parahoric groups are a particular class of these bounded groups. As I told you, a parahoric is one which contains the conjugate of an Evahori. And the theorem of Brouwer-Heinrichs is that if you look at these bounded groups coming from these concave functions, then they're all schematic. So that's important. That's why this is important to have this concavity condition. And the concavity condition also is forced when you try to write out the fact that, what is the group law inside this group. And so the concavity condition will be crucial for writing out the correct group law when you write out the multiplication operation in MF. So this is one of the key theorems in one of their very big papers in 1984, that we are really interested in these group schemes coming from, these groups coming from these concave functions. Now let me just revert back to a part of the story why we are interested in all these things. I mean, at least for people who know all this subject that I'm going to talk about. Let's start with the Fuchsian groups, which is the example that I'm looking at is with 2G generators, G being the genus of the Riemann surface in the usual study. And of course, I'm also fixing some finite order elements, C1, C2, Cn. The Fuchsian law tells us that the product of the commutators times C1, C2, Cn is 1. And each of the Ci is also a finite order element. So this is what is called a Fuchsian group of elliptic type, elliptic fixed points. It acts in the upper half space, and the quotient of which mod gamma is a compact Riemann surface with the marked points. There are these fixed points coming from these finite order elements. The images of that will be some marked points. You can just call them x1, x2, xm, xm. Okay, there's a bunch of marked points. So this quotient by the upper half space by this gamma gives you a Riemann surface with markings. Now let me take a representation or just a homomorphism from this Fuchsian group to the maximal compact subgroup of G. Example you can take is the unitary groups for groups of the standard SLN. But I also fix the images, the conjugacy class of the image of these finite order elements that I've started with in my groups. So this is my bunch of these finite order elements. So I fix the conjugacy classes. This is very familiar ground. We are in the parabolic bundle setting, except that I'm working with an arbitrary G in this case. And assume simplest case, I'm assuming almost simply connected. One of the facts that one can start even by at this point is that the conjugacy, if I take a group G and look at the complex scale, look at the maximal compact. All elements of the maximal compact is semi-simple actually. And if you look at conjugacy classes of elements in KG, then one can identify all that with a certain subset of the affine apartment that I mentioned. This is called the affine apartment is AT, and there's a natural subset which I call the while alcove, which is something like a fundamental domain for the action of the so-called affine while group on this apartment. So I'm just trying to say that conjugacy classes of elements of KG are giving you points of this affine apartment. These points theta that I mentioned in my definition here, in this definition, one of the interesting things is that because there is an affine while group action and the alcove is the fundamental domain for that action, my parahorics that I'm talking about, that is parahorics are bounded groups which come from the concave function of type 1, coming from points of the apartment. They can be essentially points of the so-called alcove. You don't need to go to all, they are up to conjugacy determined by what's happening in the alcove. So alcove is, even not all points of the alcove are essentially only a so-called barycenters of this alcove. There are therefore only finitely many parahoric subgroups for a given up to conjugacy. So the conjugacy classes of elements in KG, they correspond to points of this while alcove. So the moment I have this representation and this data of conjugacy classes, a bunch of conjugacy classes in KG, I immediately see that there is something to do with bounded groups of my kind. So I don't, as I said, to define a while alcove, I need more machinery. And so I'm looking at the affine apartment E, which I look at, and it's a fundamental domain there. Any questions up to this point? Or is it too abstract? Okay. As I said, conjugacy classes of parahorics are indexed by points of the alcove. So fixing conjugacy classes for rho Ci gives me a bunch of points of this alcove or apartment here, and hence certain schematic subgroups which I'm calling P theta I inside GK. Notice that this K should be just this Laurent series here. Okay. So because these are schematic subgroups, there exist natural group schemes on spec A which correspond to each of these theta i's, and I can glue these group schemes. So at each of these, I call them x1, x2 here. So z1, z2, these markings on x. Each of these is like an analytic disk. I mean, I'm looking at the formal power series ring in that disk here, and I'm just looking at these group schemes associated to these conjugacy classes and these points here at these points, and I look at the corresponding group schemes because each one is a schematic subgroup. It gives you a group scheme and a affine group scheme. So these group schemes have the property that over the fiber over capital K, they are actually just the product. These are generically split, isomorphic to G cross K. So these group schemes should be thought of as a picture like this. All the fibers outside the marking or outside the close point are just the group G, and these group scheme actually degenerate to usually to non-reductive groups in the closed fiber. Non-reductive groups means that it should have a big unipotent radical. Examples of non-reductive groups are parabolics, but here there's a smooth group scheme, so this dimension of this closed fiber is the same as the dimension of G. So you're going to get a list of natural non-reductive groups which are coming up here along with these parahorics. So what we are having is, if you fix a Fuchsian group and a representation with fixed conjugacy classes, I automatically get a bunch of group schemes around each of these marked points, and I can glue it to the constant group scheme because generic fiber, all these group schemes is G cross K. I glue them together and I get a group scheme. I'll just call it G theta with an underscore or a bracket here. So this is the data of a group scheme on the whole Riemann surface. And there's an analog of the Narasimhan-Seshadri, Mehta-Seshadri theorem here that I look at homomorphisms from this Fuchsian group to the compact group with fixed conjugacy type, which is what Seshadri would call type tau, modulo the compact group up to scaling action. Then this real analytic manifold actually gets natural complex structure by identifying, you can construct this moduli space of semi-stable torsors or principal homogeneous spaces for this group scheme that I've constructed here by gluing this. Notice that if you change the gluing, the spaces will not change. Okay? Because torsors are essentially understood in terms of locally they look like the group schemes. So what gluing data I use here is material. Stacks are all the same. So this theorem that I've written here is with Seshadri in 2015, that we can identify this left-hand side, which is the analog of the fundamental group representations, unitary representations of the fundamental group. And of course, under these, you can talk about irreducible homomorphisms from gamma to kg, and they correspond to the stable objects on the right-hand side. And this is a complete analog of the classical theory of Narasimhan Seshadri and Mehta Seshadri. The interesting thing here is that if you choose these conjugacy classes carefully, then you will have to go outside the category of G bundles to understand the story. It's not just G bundles with parabolic structures. These are genuinely non-G-like group schemes and principal homogeneous spaces under that. That's the important part. And what sort of conjugacy classes you would choose determines the point that on the so-called alcove that this theta is determined. Okay, there is a complete picture of what's going to happen. So the important perspective that comes here is that we can identify the classical Parabolic subgroups as local automorphism groups of equivariant G bundles. And this is the new feature which comes by which one can then make these group scheme identifications and build this whole story. So this is a slightly, understanding groups as automorphism groups is always an interesting feature because, classically, most like Erlangen story, Felix Klein. So these Parabolic groups are also viewed as local automorphism groups of equivariant G bundles. I'm not elaborating this, but it's there in my paper. So these Ruha-Ritz group schemes of type 1 they can be obtained as Weyl restrictions and invariants. It's something like an invariant direct image. If people are familiar with what Seshadri does for parabolic vector bundles, then these group schemes have a parallel there. You can realize these Ruha-Ritz group schemes as invariant direct images. In direct images, the Weyl restriction of scalars, and invariance is the usual invariance. There's some finite group actions here. And so there is a very beautiful analog between parabolic theory and Ruha-Ritz group schemes, at least for paraholics. The important part to know is that the non-paraholics will not come like this. Okay, so I change tack here and go to another application of the story. So let's look at this part of the story here now. I'm interested in the problem of degenerations of moduli spaces of G bundles. So what do? I'm looking at a picture of this kind where I have this smooth curve degenerating to a nodal curve, irreducible nodal curve like this. This is my picture X over S. S is the BVR, KT, if you can think of it, Parse is in one variable. The closed fiber is the irreducible nodal curve. Can you hear me? Hello? Hello?
Yes, we can hear you.
Yes, we can hear you.
Yeah, sorry, there was my network showed a fall in the thing, so I thought I'm losing mine. Okay, so this is the closed fiber X naught, and these are the smooth curves of genus G that I'm fixing. And I'm looking at a family here. I'm interested in constructing a stack, maybe, over S associated to this family X, so that the generic fiber of the stack that is over X capital K. K is you can think of K as the generic point and the function field of this KT here. So the next K, and I want to construct a flat degeneration of this. That's the important part here. So this is an old question. When G equals GLN or the orthogonal group of the symplectic group, Falting's later, and this is constructed using Seshadri's very old idea of going back to his work on Picard with the D'Souza's work and Seshadri, Oda Seshadri, and so on and so forth, by adding torsion-free sheaves. That is, in the case of GLN, I can look at principal GLN bundles as vector bundles, which is the advantage for GLN, that I have a sheaf theoretic picture there. GLN bundles are vector bundles, therefore also locally free sheaves. So I can use torsion-free sheaves to expand my category and go to the nodal curve situation and compactify them. Faltings uses torsion-free sheaves with degenerate quadratic forms or symplectic forms and has a similar theory. So you can construct flat degenerations by doing this kind of thing, which is somewhat of a geometric invariant theoretic construct. Okay, Faltings uses slightly a small variant of his own for the instead of GIT. But let me mention that there is no analog even for something like G equal to SLN for n bigger than 2. N equal to 2, it is a symplectic group, so you can still get it. But for n bigger than 2, there's no way of doing this. So what's my approach here? Following ideas of Giesecke, Nagaraj, Seshadri, and Kaus, what one does is you take this original family that I started with, this family, with a degenerating to a nodal curve, and replace it with families of this kind for running D. I mean, D varying here. What is this XDS? So XDS is a curve family like this, which looks like the same old, the generic fiber is not changed. The generic fiber is the same here, over K. The closed fiber, instead of the nodal curve, I replace it with the reducible curve now, which is what is called a semi-stable curve. There is a bunch of P1s which can meet at 2 points, unlike stable curves. The normalization here at, so I mean, examples of semi-stable curves are this curve, for example, it meets it at 2 points. So this is non-trivial automorphisms, non-finite automorphisms. So Giesecke's idea, later on taken up by Nagaraj, Seshadri, and Kaus, is instead of working with a single nodal curve at limit, work with a bunch of semi-stable curves whose stable model is the original nodal curve. So I'm looking at families whose stable model is fixed, which is this. And this D will not go, I mean, there's some boundedness which will come, which is natural for the question that we look at. So when I look at XT here, I'm looking at the normalization with the D minus 1 P1s attached here. And I'm interested in solving the problem for an arbitrary, simply connected G. So what's the strategy? The strategy is not to consider G bundles on the limit curve. See, like in torsion-free sheaves, we need to go to a different setup. And the interesting thing is that instead, I construct a group scheme or a family of group schemes. I mean, these are group schemes which is indexed by a bunch of taus, which is going to come, what I call local types here. This is some finite collection. So you have a finite collection of group schemes on these curves XDS for running D. Again, and D is also bounded. And these are smooth group schemes on this surface now. So I'm having a two-dimensional, this is a surface. There's a two-dimensional ring here, which with a divisor with normal crossings, which is the closed fiber, is a quasi-projective surface. The base is just a DVR here. So on this quasi-projective smooth surface with a normal crossing divisor, I construct a group scheme so that when restricted to the generic fiber, this part, it is the old G cross K, the generically split case. But when the group scheme degenerates to the divisor in the boundary, so I'm looking at the degeneration of this divisor to the boundary components. So the first condition that I'm putting is outside the closed point of the base, the group scheme restricts to the split group scheme. That means it should be just this product. So I'm just looking at the top. And the group is degenerating now, but how does it degenerate? The law is that at the irreducible components of the closed fiber, which is the normal crossing divisor, I look at each irreducible component is going to give me a height 1 prime ideal on this quasi-projective surface. So I can localize it, localize the ring there, functions, and I get a discrete valuation ring at each of these height 1 prime ideals. I'm back to my discrete valuation picture. My group scheme is such that at all these discrete valuation rings, restricted to these discrete valuation rings, it should be the classical Broughart group schemes. But these group schemes have extended not only to the height 1 data, but also to the corners. So that is the extra bit of this group scheme that one is having. I'm having a two-dimensional ring now. So you could, in principle, concentrate on just this piece here, which looks like an A2, or its completion at the origin. And I'm constructing a group scheme here, which degenerates in this direction at these two height 1 prime ideals to give you classical Broughart group schemes, but one is also extending the group scheme all the way to a height 2 prime ideal, a codimension greater than equal to 2 subsets. So that data is, so this is a finite collection of these group schemes which come in and help me solve the question. So I call these group schemes in my paper as 2BT group schemes because they are like a Brouhatter's group schemes, not on a discrete valuation ring, but a regular two-dimensional ring. I can take the completion here, but I mean, yeah. So I'm looking at power series ring in two variables, for example. And what are the limiting objects? Instead of working with torsion-free sheaves, the limiting objects should be thought of as what are called Giesecker objects. That means I'm looking at a semi-stable curve. I'm having a certain group scheme, which is the limiting group scheme. So my group scheme here, the G's are here. The G's go and become a non-reductive group scheme on this closed fiber. So you have these closed fiber group schemes, which are non-reductive groups, and certain kind of torsors, which are called admissible torsors for these group schemes. So these triples will be my object for the moduli problem that one stack that one wishes to construct. And then there's, of course, all theorems that one has to prove about properness and semi-stability and so on and so forth. And all this can be done, and it's a long story. Yeah. But I'm just telling you that a natural entry of what is called a 2BT theory came in my paper here. So that led to the question, which is now what's the main theme of my talk today was. Now I'll talk about the theme in the title. So how much time do I have? 10 minutes or 15?
Yeah, you have 16, 17 minutes.
Okay, very good. Okay, good. So I'll talk about the theme. Which I mentioned in the thing, that this is joint work with Yashwanidhi Pandey. Okay, so what's this thing? So I'm going to work. As I looked at this A2 picture here, and the rest is kind of a globalization of this construct. So one is interested in, if you want to generalize classical Brouhatter's theory, there is a history to this. So in Brouhatter's, the main paper, they do talk about how to look at this, how to construct group schemes over A2, which have this kind of property. And they give some simpler examples, but not the ones which I look at in my paper. So I did not know about the existence of this paper, this part of the paper when I wrote my thing. So, but my group schemes come more in the setting of the problem that I was looking at. But Brouhatters do address this question in a small section in their paper, where they ask or suggest how possibly one could look at this question, at least over A2. Okay, so it is, in that sense, historically important to ask this question over bases which are not just discrete valuation rings, and ask, so what is the theme? Let me just go to the page here and tell about the theme that I'm looking at. So I'm looking at say A2, and I'm looking at, as I said, so I'm looking at K, say Z1, Z2, power series ring. So I have these two height 1 prime ideals, and therefore I have discrete valuation rings at these 2 points. So if I begin with data at these discrete valuation rings, which are classical Brouhatters of some kind, coming from some bounded groups, maybe parahorics, say G theta and G theta prime, at these 2 localizations. And I also assume that away from the divisors, it is a split group scheme. So this is in my same assumption. Say it is G cross K. K now is the complement of the divisors. I mean, just look at the open subset where, so this is G cross U, where U is A2 minus the hyperplanes. So if you look at this picture and look at the constant group scheme here, and these group scheme also I'm assuming is generically split. So I'm taking the constant group scheme and allowing it to degenerate to the height 1 prime ideal here, and this to height 2 prime with constraints. So with some constraints of that it should degenerate as a parahoric or something like that to those height 1 data. That means I would have extended this group scheme by gluing this constant group scheme with these group schemes at the height 1 data, and therefore I would have had a construct of something on A2 minus the origin, a group scheme here. So the problem now is, can one extend it as a flat or a smooth group scheme, as an affine group scheme? All these group schemes that I'm looking at are actual affine group schemes. Can I extend it to the origin with the same property of being either affine group schemes? And it's a genuinely hard question, because schematic closure constructs can be done with group schemes, but usually you lose flatness if you are not very careful. And classical Bruhatich theory is also constructed by seeking some sort of schematic closures. You construct the group scheme for linear case, choose an embedding of G inside GLN, and take schematic closures, but their flatness is automatically preserved because your base is a discrete valuation ring. Here, my base is a dimension bigger than 1. So technical problems of that kind will start popping up. Of course, there is a genuine hardness to understand what's going to happen in the corners, whether one can actually extend it at all. And so this is the theme that we are following, not just for A2, but more generally for the affine space AN. And I have a bunch of standard hyperplanes HI here. And so one is, the way one would put it is that one is giving data at the height 1 prime ideals given by these hyperplanes. And the data, if we put the constraint of the data at the hyperplanes with group schemes of the kind that we started with, which is one-dimensional in nature, can one extend to an n-dimensional regular local ring and construct either smooth, affine or quasi-affine group schemes. So this is the phenomenon that comes up. Any questions, or is it too technical? Okay. So I work with.
So I have a question. Sorry, can I ask something?
Yes, please.
So this along the two axes you have two representation of some finite group, right? Along the this one and the other one.
That's right. Yes, you have two representations given by the θ1 and θ2.
θ2. So is in the corner in the intersection, is it some kind of combination of those two?
It's a very non-trivial combination. The first thing that I want to say is, even though if you start with some very nice data like Parabolic here, the reason why I spoke about concave functions, or now at least we can go back on hindsight and say that Bruhatich might have had a high-dimensional picture in mind, is that at the corner, even though you may start with something like Parabolic here, you land up with something which is a concave function here. And this concave function in this corner, in this case, happens to be simply mr θ1 plus mr θ2, the concave functions that I spoke about earlier. Mr θ1 is the greatest integer function for r theta. This is fr. So this kind of, and these concave functions are not simple at all. I mean, in the sense that we give examples in the case of G2, exceptional groups where these concave functions don't even come anywhere near the parabolic or even the bounded domains, but they go outside. They are genuine concave functions in the most general setting of Bruhatich. So they don't come from any representations or anything like that. Okay, but they are these. When I say here, I mean I'm to say that the fiber of the group scheme. That is, if you construct this group scheme on A2, here at the fiber and all, one knows by classical theory. That means on an open substrate. At the corner, that means if you approach this and look at it, say a discrete valuation ring with origin as the corner here, a diagonal, for example, and restrict this group scheme here, you got a DVR here, and this group scheme is a group scheme associated to a bounded group coming from a non-trivial concave function like this. So at the intersection of the hyperplanes, you always get concave functions. That's the key point of the story, that you can't avoid, even if you stay at the height 1 prime ideals in good setting, when you go to lower depth or higher depth, higher codimension points, you get you go out of the parabolic theory, you go into what is genuinely the full generality of Bruhatich theory. So let me make my quick definitions here. As I said, this work with Yashwanidhi Pandey. All this, whatever I'm saying, although I've written it for complex numbers, the coefficient O can be a discrete valuation ring with residue field large characteristic. Largeness of characteristic is forced by a certain work of mine with Deline and Paramu, where Coxeter numbers come in to understand unipotent groups here. So there is some important cell structures for these groups, and one has to extend the unipotent groups in a nice manner across codimension bigger than or equal to 2. And here lots of enjoyable algebraic geometry coming from Reno's work come into the picture. Anyway, my ON is now a part series ring with coefficients in O. I can call Z0 to be the uniform measure of O, because O is already a DVR here. The large characteristic is forced. And then Kn is a fraction field of this thing, and that's going to be my open subset that I'm working with. Now for this entire bunch of uniformizers Z0 up to Zn, we can associate, for each index I, we associate a concave function Fi. This should be phi tilde. And they define what is called n concave function, the tuple into the Rn, where n is I'm looking at the number of variables here. So an n concave function is just it. And to this, we can associate an n bounded subgroup of this group GKN. GKN is just G with entries in O, round bracket, the quotient field. Okay. So I can associate an n-bounded group like this. I'm looking at the torus part intact. For the root elements, for the root groups, I'm looking at products of the uniformizers, but with powers these concave functions. This is a very simplistic and natural definition. So this is an n-bounded group. I'm associated to an n-concave function, and a complete generalization of what's happening in the one-dimensional case. And again, we can call a subgroup Q of GKN a schematic subgroup if there exists a connected smooth ON group scheme G of finite type with the generic fibers G cross Kn, such that the valued points at the ON recover back my bounded group. So these are the schematic subgroups as an exact generalization of what Drouard gets to. Okay, except that the higher dimensional base makes scheme theory more complicated. So we can again have three types. So concave functions, n concave functions are type 1. Type 2. Type 2 means that my omega is not a singleton but a region, a bounded region, and a bounded region could have. If you can even assume it's convex with a hull of a bunch of points, but the bunch of points makes it complicated. So you have these concave functions, and then of course there's a general type, which is the third one. You can call it the type 3 or the general type. So what is the theorem then? So for any bunch of concave functions of each type, that means I'm, instead of putting paraphorics here to complete the correct theory, at each of these things, I put a GFI, a group scheme coming from a concave function. As I told you, giving a concave function gives me a bounded group, and to a bounded group for the discrete valuation ring, classical Drouard theory gives me group schemes here like this. So if I give you group schemes at the high-tone primordials, can I extend it to a group scheme? And the theorem is that in type 1 case, you can extend it to an affine group scheme, whereas in type 2 and type 3, it is at best only, a priori only, a quasi-affine group scheme. So this is the new difference. Of course, these are nice flat group schemes. That's the interesting part. And there is the type 1 theory is very much like the parabolic theory. And once again, one can use Kawamata covering lemma and Weyl restriction of scalars and such things to recover the type 1. But the theory has to go through for type 2 and type 3. And type, it's like some sort of you have to use the type 1 construction to build the type 2, and you have to use the type 2 to build the type 3. So it's like some sort of a bootstrapping story going on here. The interesting point is that these group schemes, they are also schematic in the sense that means that we prove that these n-bounded groups coming from these concave functions are schematic. That means these group schemes realize these bounded groups. That means the ON valued points is giving this, and they are more or less uniquely defined by various properties. Coming from so in some sort of you fix a data at the height 1, and then you construct a group scheme adapted to this data at the height 1. Some sort of a Hartog's principle in a very basic sense, but complications come naturally. And the valued points are being determined by what's happening at the height 1, because please notice that this data of concave functions is being done at the height 1, and this valued points being determined by this is follows from a theorem of Weil, which tells you that if the base is normal, the sections of a nice smooth group scheme, a fine group scheme, or quasi-affine group scheme in this case. I mean, these smooth group schemes are all captured by what's happening on height 1 prime ideals. So that's all. I mean, I'm just trying to say that there are, I hope, many more applications for this kind of story. But this is a novelty, a new thing which comes up motivated by problems on degenerations and things like that. So I guess that's all that I wanted to say. Thank you very much. Any questions?
So have you also put so much correspondence like orbifold?
Sorry, orbifold theory?
Yeah, like parabolic interval high dimension we have correspondence.
Yeah, I know. See, in the Kawamata, see, in the higher dimensional case, one will have natural correspondence here immediately without any problem. And one can relate the stack of parabolic bundles on a smooth projective variety with normal crossing devices. That's almost immediate. Interesting thing is that this data will tell you what's happening at the corners. What sort of fibers? See, they are no longer parabolic. They are really complicated data, right? Coming from such concave functions. So there is a paper of Niels Bohr for GLN, and I think what one is trying to say here is that you get interesting data on the corners coming from these concave functions. I mean, group schemes coming from the. See, what I'm trying to say is, if you take a smooth projective variety with normal crossing devices, and you give some weights structures here, and you're interested in asking the question of classification of one with a certain type of groups on such a variety with the divisor D. Okay, there is an equivariant theory, I'm saying, which is natural, and it also tells you what's going to happen here, which is not at all visible. That means if I look at my torsor here that I'm looking at for these group schemes, someone constructs here, the fiber of the torsor is the fiber for the closed fiber of, that means I'm having a discrete valuation ring and I'm having a group scheme associated to a concave function. The closed fiber is a non-reductive group whose Levy part is determined by the concave function here. I mean, one can write the root system for the Levy part given by the concave function. So the torsor at the closed fiber will be a torsor for this closed fiber of this group scheme. This is a non-reductive group scheme. And that data will come as a part of this structure that we're looking at. That means the invariant push forward of a principal G bundle will have a more complicated structure in the corners, and which are all dictated by what we have just written down here. Is it answering your question? Yeah.
Other questions?
Yes, I had a question. So, Balaji, thank you for the talk.
Yeah.
So, I wanted to know that. So, yeah, as you mentioned just when we were talking about the multi-lie stack, that you need the rank to be 2 for the symplectic group. But can you take many nodes? That should be fine.
In principle, at least for this question, I need a stable curve, and one could do this for any stable curve. I mean,
okay.
Yeah. Eventually, I would like to answer this. Eventually, I will answer this question for mg bar, but technically there are some complications. But if you just take a one parameter family with a closed fiber stable curve, for example, picture like this, something like this,
right?
Then it's you can have a similar theory, and at each of these nodes, you will attach chains of P1s and group schemes associated to around each of these points, and then you'll have a theory of two BT group schemes for chains at those points, and the stack question automatically gets solved.
So have you already done this, or you think that eventually this will be done?
I believe that, I mean, one can do it. I wanted to do the whole thing for mg bar, which is a little more complicated, and that's what I'm doing now.
Okay.
So yeah, for the reducible curves, I thought I'll write it first, a simplest
Right.
case. And what's happening here, the reducible curves is slightly simpler. The
Right.
reducible case is more complicated. So to make it a little more palatable, I'm planning to write the reducible curve case now. Because since my last manuscript, I believe certain simplifications I can see, and this is a huge paper. I don't know how many people will read it. So I want to write something on the reducible curve case. Yeah.
Okay. Thank you. Thanks a lot.
Okay, if there are no more questions, let's thank the speaker for the great talk.
Thank you. Thank you very much.